Good afternoon, everyone. My name is Kendra Rivers. My research mentor is Dr. Kevin Daniels. My topic is simulating molecular sieve-based gas sensors on 2D heterostructure using the COMSOL software. My research goals were to model the electric interaction between the materials and to model the molecular sieving. Here we go. Okay. So gas sensors are needed in different industries to map gas toxicity, such as greenhouse gases, VOCs, and viruses. Traditionally, gas sensors are low cost, robust, and selective. However, the TMOs need high temperature in order to operate, which slows down its response and recovery time, which also can impede on its selectivity. So our proposed gas sensor aims to solve this problem. This model here shows the silicon carbide, the bilayer graphene, and the manganese dioxide. The graphene will ensure sensitivity and the manganese dioxide will ensure selectivity. Two main principles we want our environmental gas sensors to have is high sensitivity and high selectivity. Graphene and manganese dioxide complement each other, but what one material lacks and the other makes up for. Graphene is a very thin and strong material that is highly conductive. It has a high surface area that allows every atom to be exposed, which creates the sensitivity in graphene. Here you can see a molecule moving towards graphene. As soon as it lands, the graphene is very receptive and able to create a quick electronic transfer. However, it is sensitive, but it's not selective. Selectivity is very important for a gas sensor to target the specific gas molecules. Manganese dioxide has a unique structure, which has an interlayer spacing of 7.4 angstroms. For our targeted gas molecules, we want 4 angstroms, which is an NO2 gas molecule. The molecular sieving process that occurs in the interlayer spacing rejects large molecules and allows small molecules to pass through quickly. Here you can see a model of a gas sensor that we have. The top is a gold contact here. The green is the manganese dioxide. The black layer is the graphene, and the bottom layer is the silicon carbide, which just acts as a base. Our experimental results show fast response times, which under 4 seconds, which is extremely fast compared to other TMO gas sensors who have reported within 100 seconds response time. The two main sensing mechanisms that I am focusing on in my COMSOL models are electronic effects and structural effects. The electronic effects show the fast charge transfer within the heterostructure, which has a high carrier mobility due to the built-in potential. The structural effects shows the interlayer spacing, which I will later show you in the manganese dioxide layer. Here you can see my COMSOL model for the built-in potential. I have created just a heterostructure of the manganese dioxide and the graphene with the gold metal contact on top. The lower layer, the thin layer here is the graphene, the middle is the manganese dioxide, and the top is the gold. On top, you can see the differences in the work function. The lower the difference is, the lower the barrier gate or the barrier height here is. And that means the electrons have an easier passage to move into the material that has less concentration, which is why you see a lot of variation within the manganese dioxide layer, because it is a lower concentration compared to the graphene and even the gold. The graphene and the manganese dioxide are p-type semiconductors, which carry more holes. So you'll see a larger difference with the hole concentration in this model. Our last model we created shows the molecular sieve, which is the structure effect. The molecular sieve is the particles moving from one inlet to the outlet. Here you'll see the particles released and moving into these interlayer spacings. We are still true to size with having a space of 7.4 angstroms. and we're trying to model the particles movement through the layers. You can see a green line here in the beginning of the interlayer spacing, meaning that some molecules are stuck at the beginning while others still travel through. We also had to use a boundary condition of diffuse scattering just to make it more realistic, because when the molecules are moving into these layers, they are ringing around, not just passing through with ease. Also, because of the manganese dioxide material is highly catalytic, so some molecules will move through the layer, but it also will still conform to the size or stay in the layer. So our two main principles we wanted to highlight is high sensitivity with the graphene, which was shown in the Builtin model, and high selectivity, which is shown in this model. Thank you for your time. I appreciate you listening to this presentation.